Hi friends, I am Dr. N. Sangari, Associate Professor in the Department of Chemistry, the Standard Fireworks Rajaratnam College for Women, Sivakasi. Dear learners, today we are going to learn the fundamental concepts covered under the heading Photochemistry. Okay, first we will know the definition for photochemistry. Photochemistry is the branch of chemistry concerned with the chemical effects of light. The study of chemical reactions, isomerization and physical behavior that may be caused by the absorption of ultraviolet, visible light or infrared radiation are called photochemistry. There are two important laws governing the entire photochemistry field. They are Groth-Draper law, Stark-Einstein law of photochemical equivalence. First, we will see about the Groth-Draper's law, which is also known as the first law of photochemistry. This law was enunciated by Groth and Draper in 19th century. They found that all the light that was incident on a sample was not effective in bringing about a chemical change. Only those radiations which are absorbed by a reacting substance or a system are responsible for producing the chemical change. And here the picture depicts well about the Groth-Draper's law. The reactant molecule A upon absorbing the photon of energy h nu get into the excited state, and we call that molecule as an excited molecule, which may give away the desired product B. The second law of photochemistry, which was enunciated by Stark-Einstein law, is also known as the law of photochemical equivalence. The second law of photochemistry, known as Stark-Einstein law, states that each photon of light absorbed by a chemical system activates only one molecule for the subsequent reaction, and therefore this principle is often called the law of photochemical equivalence, and it was formulated by Albert Einstein during the development of his quantum theory of light. So as we said, we have to learn the quantum yield or quantum efficiency, how far the absorbed photons yield the product will define quantum yield. Therefore, it has been shown that not always a photochemical reaction obeys Einstein law. The number of molecules reacted or decomposed is often found to be markedly different from the number of quanta or photons of radiation absorbed in a given time. So, we define a term called quantum yield or quantum efficiency, which is a ratio of the number of molecules reacted or formed per photon of light absorbed to the total number of photons absorbed. For a reaction that obeys very strictly on Einstein law, then one molecule decomposes per one photon absorbed. Therefore, such a reactions, the quantum yield will be equal to 1. Similarly, when two or more molecules are decomposed per photon, then the quantum yield will be greater than 1, and the reaction has high quantum yield. Consequently, on the other hand, if the number of molecules decomposed is less than 1 per photon absorbed, then the reaction has the quantum yield less than 1. There are other two laws which are important in understanding thoroughly photochemistry. They are Beer's law and Lambert law. Beer's law was stated by August Beer, which states that concentration and absorbance are directly proportional to each other, whereas Lambert law stated that absorbance and path length are directly proportional. And these two laws, they are combinedly stated as Beer-Lambert law, which read as, for a given material, the sample path length and the concentration of the sample are directly proportional to the absorbance of light. We may express this Beer-Lambert's law with the equation A is equal to epsilon into L into C, where A is the amount of the light absorbed for a particular wavelength by the molecule. Epsilon is the molar extinction coefficient. L is the distance covered by the light through the solution. And finally, C is the concentration of the absorbing species. And this law has certain limitations. Beer-Lambert's law is not valid when non-monochromatic radiation is used. Secondly, if the temperatures during the measurement, the law could not be held. And finally, the law is applicable only to dilute solutions. We may not use the same law for concentrated solutions. The figure on the right hand side explains the Beer-Lambert's law. Okay, next we will learn what are all the consequences of light absorption. The consequences of light absorption is well explained by Jablonski diagram. The diagram is given in the picture. You can see the various singlet states and triplet states. All the S states are representing the singlet states and all the T, they are representing the triplet states. And in here we got IC, ISC, R, F and P, which are representing respectively the internal conversion, intersystem crossing, relaxation, fluorescence and phosphorescence. We will see it one by one. Here in the picture, one important feature is conveyed, and that is more than one electronic state is likely to exist for a given molecule. 6 are drawn. I told you, no, it is only 6 are drawn and labeled in the diagram. Each electronic state will have a group of vibrational and rotational states. They are depicted by the blue lines above each state marked. Transition between the electronic states often occur to higher vibrational levels, which then relax to lower levels by collisional loss of heat. The excited states may be classified as singlet or triplet based upon their electron spin angular momentum. The electrons in most non-metallic organic compounds are paired, so ultimately they will have opposite spin in the bonding and the non-bonding orbitals, resulting in net zero spin diamagnetic molecule for the ground state. Such states have single energy state in an applied magnetic field and are called singlets. Electronic states in which the two electrons with the identical spin occupy different orbitals as per the Pauli's exclusion principle will have a net spin of 1, which is obtained by multiplying the spin quantum number half into the number of electrons 2, which is give us the result as the net spin as 1, and those molecules are paramagnetic in nature. In a magnetic field, such states have 3 energy levels, +1, 0 and -1 levels, and are called triplets. The distinction between singlet and the triplet state is very important because photon induced excitation always leads to a state of the same multiplicity, that is singlet to singlet or triplet to triplet. Since most ground states are singlets, this means that the excited states initially formed by the absorption of light must also be singlets. So we have various processes as I depicted in the picture, IC, ISC, R, F and P. What are they? First we will learn the internal conversion. What is internal conversion? The internal conversion of the excited states to lower energy states of same multiplicity takes place rapidly with the loss of heat energy, which could be called as relaxation. Alternatively, an excited state may return to the ground state by emitting a photon by a radiative decay process. The conversion of a singlet to a lower energy triplet state or vice versa is termed intersystem crossing, and is a slower process than the internal conversion. Radiative decay from a triplet state is called phosphorescence and is generally quite slow. The approximate time scales for these transitions are given in the following table. Here in the first column I have noted down the processes, the second column the transition occurring among the various states, and in the third column I denoted the time taken for each of the processes. Here the important processes, light absorption takes place from singlet and it may lead the molecule to any excited state. Then internal conversion within this electronic states of same spin multiplicity. Whereas intersystem crossing, if you know down, there is a transition from the singlet to the triplet state. Okay. In the same way, phosphorescence also triplet to the singlet state. So these are all the time scales. The non-radiative decay noted in the last row may take place by intermolecular energy transfer to the different molecule. This collisional process is termed quenching if the focus is on the initially excited species, or it could be a sensitization if the newly created excited state is of interest. So this diagram is a separate Jablonski diagram which explains the processes of fluorescence and phosphorescence. So these are all the various terms what we have defined in the form of diagram in Jablonski diagram. First, the molecule absorbs a photon jumping from the ground state with the singlet 0 to a higher excited state which is of spin multiplicity 1. So they are called S1, S2 and etc. So this process is a very fast process. That's why in the table we noted down it occurs as 10 to the power minus 15 seconds. The next comes the vibrational relaxation. The molecule quickly loses excess vibration energy to the surroundings, moving to the lowest vibrational level of current electronic state. So it will be either internal conversion IC, a fast non-radiative transition from higher excited singlet state to a lower singlet state, S2 to S1 or S1 to S0. Intersystem crossing, it is a transition between a singlet state and a triplet state. This is a non-radiative process and that changes the electron spin. A fourth one, fluorescence, a radiative process. The third process, fluorescence, a radiative process where the molecule in the excited state S1 emits a photon and returns to the ground state S0. This process stops once the excitation light is removed. The final process, the fourth one, phosphorescence. It is a slower radiative process where a molecule in the excited triplet state emits a photon to return to the ground state S0. This delayed emission continues after the excitation sources stand off, as is seen glow in the dark materials. Let me distinguish the processes, fluorescence and phosphorescence. Fluorescence is a decay period is much longer, whereas the phosphorescence decay period is very short. And fluorescence, it is a radiation emitted in the transition between the states of different multiplicity, whereas phosphorescence is the transition between the states of same multiplicity. Fluorescence is not absorbed in the solution at room temperature, but phosphorescence can be absorbed in solution at room temperature. If the spectrum is a mirror image of the absorption spectrum in the case of fluorescence, whereas phosphorescence spectrum is not a mirror image of the absorption spectrum. And fluorescence is exhibited by some elements in the vapor state. Phosphorescence is rarely absorbed in gaseous or vapors. Some examples of substances which fluoresces are uranium, petroleum, some organic dyes, chlorophyll, calcium fluoride, etc. And similarly for phosphorescence, zinc sulfide, sulfates of alkaline earth metals. Thank you, learners. Hope you all understand the basic definitions, the laws and the consequences of light absorption through Jablonski diagram well. Thank you.